Welcome to It Is Raining Space Dust for SCUDEM X 2025. We are Team 1001 from Denmark High School in Alpharetta, Georgia. I'm Vivek Venigalla.
I'm Naunidh Singh.
And I'm Aadhav Thaniga, with coaching support from Dr. Gregory at Georgia Tech. In this video, we'll show how we built a mathematical model to turn tiny grains of cosmic dust into a kind of forensic tool for reconstructing what happens high above Earth's atmosphere. Our agenda today includes the problem, assumptions, formulation, results, the backward model, and a conclusion tying everything together.
Cosmic dust constantly rains down on Earth. Grains can range from a few molecules up to about 1/10 of a millimeter. The challenge in problem A is that if we dig up dust particles in a layer of rock or ice on Earth, can we use those grains to learn about how they entered the atmosphere? To get there, we need to first understand how a single grain falls through the atmosphere. Then we can scale up to many grains and ask, can we run that backwards?
So we organized our work around three goals, which transformed into parts of the model. Compute the 3D trajectory of a dust grain entering from around 100 kilometers altitude using gravity, drag, and ablation. Include randomized wind and simulate a distribution of points falling through the atmosphere to find the ground distribution. And finally, to build an inverse model to see whether we can use the end distribution of particles to find the initial distribution.
Imagine our dust grain as a ball falling towards the ground. At first, gravity points straight down. As it picks up speed, the atmosphere pushes back with drag opposite the direction of motion. At the same time, wind can push the particle left or right, or even at an angle. As a result, we get a velocity vector v, opposite to the force of drag. Finally, depending on air density and velocity, the particle also burns up in the atmosphere through ablation. This changes the mass.
To keep our problem feasible, we made a set of modeling assumptions to follow. Each dust grain is a sphere with uniform density representing ordinary chondritic material. Grains are neutral, so we can neglect magnetic and electric forces. Radiative forces are tiny compared to drag at these scales, so we ignore them. In addition, grains ablate smoothly without fragmenting, and we consider gravity to be fixed at 9.81 meters per second squared. The grains enter at the Kármán line, which is 100 kilometers above the Earth, and at the scale we treat local weather as a perturbation on a climatological wind profile, which prioritizes the stochastic effect of wind over large-scale patterns specific to geography and time. The curvature of the Earth is significant at the scale of the simulations, and the entry velocity of grains ranges from 12 to 16 kilometers per second, and the radius varies from 5 to 5,000 micrometers. We chose these assumptions because each is supported by observational studies and adds only a small correction compared to drag and ablation, letting us focus on the dominant physics, which is gas flow, drag, and ablation.
Now we translate the physics into equations. First we consider gravity, where the gravitational pull is equal to the particle mass times the gravitational acceleration. Then we consider three types of drag: quadratic, Stokes, and Epstein. Quadratic drag is for fast-moving particles low in the atmosphere where there is a high air density. On the other hand, Stokes drag is for a low Reynolds number which has very inviscid flow. And Epstein drag is for free molecular flow when the Naunidh number is large. At each point in the time, we compute Naunidh and Reynolds numbers automatically and from the local air density. The model then automatically picks the appropriate regime based on threshold. If the Naunidh number is greater than 10, we use Epstein. Otherwise, if the Reynolds number is less than 0.1, we use Stokes, and otherwise we use quadratic drag.
Viscosity μT comes from Sutherland's law. We use this formula for thermal velocity. Finally, we include ablation using a standard convective heating formula. As grains heat up, they lose mass, which shrinks their radius and changes both drag and velocity.
To drive these forces, we need a realistic atmosphere. In the code, we implemented the US standard atmosphere from 1976 as a piecewise function of altitude. Each layer in the atmosphere has its own temperature lapse rate or isothermal region from the troposphere up to about 85 kilometers. From these graphs and piecewise functions, we can compute the pressure and then density using the equation as shown below. The parameter values and functional forms are taken from aerospace references and educational modules on orbital debris and atmospheric modeling. So far, our particle has fallen through a still atmosphere, but in reality, winds in the upper atmosphere can reach 10 to hundreds of meters per second. In order to create a 3D wind profile, we set a baseline mean speed for in each layer and smooth it over using a Gaussian process. As well as that, we multiplied it by a random factor with a Weibull in the troposphere, a truncated normal in the stratosphere, and an exponential in the mesosphere, which creates an accurate wind model of each layer.
Here are the key parameters in our model and what we filled in for them. Values come from NASA technical reports, aerodynamics references, or peer-reviewed papers on chondritic meteorites. We validated these values across various simulations.
For a single representative dust grain of a radius of 10 to the -4th meters, entry speed 14 kilometers per second, and a 30-degree entry angle, we integrate our system numerically, stopping when either the mass goes to 0 or the altitude reaches the ground. The position plots showed that it travels only tens of kilometers horizontally, but almost a full 80 to 100 kilometers vertically, so the motion is dominated by the fall rather than sideways drift. The drag force plots show sharp spikes as the grain first hits denser air and our code switches drag regimes, then one broad peak followed by a smooth decay towards near terminal fall. Those early spikes partly reflect that our transition between Epstein and quadratic drag isn't perfectly smooth, but over the long term the overall trend still matches the expected high drag pulse and gentle coasting phase.
To make the motion more intuitive, we exported the position data from Python into CSV files and feeded them into Magnum 3D scenes. The yellow path you see is a dust grain flying along one of these trajectories. This makes two things clear. Even tiny grains can travel long lateral distances considering drag forces, and the most violent physics, peak drag and ablation, just happens just over a few tens kilometers of altitude.
Here we show an example wind simulation of how a sample trajectory bends when wind is active. Because the wind field is stochastic, the particles experience varying deflections that influence dust landing sites.
We ran multiple simulations by varying the mass and velocity of particles. As shown by these trajectories, we can see that the changes in parameters do not significantly affect the trajectories, and we've also tested these with other parameters and achieved similar results.
Now it's time to find the inverse mapping. This backward neural network model approximates the inverse function of our forward ODE system, mapping final mass and position to their original values. It is constructed from 8 sequential matrix multiplications with the hyperbolic tangent applied between them. By optimizing this function over thousands of Monte Carlo trajectories, we obtain a numerical approximation of the true inverse dynamics.
The plots show how well this backward map works. For this example, all grains start at essentially 1 point for simplicity, but wind spreads their final positions into a broad fan. This is the messy data the inverse model sees. When working backwards, the model takes this final distribution and tries to predict the initial distribution, as seen here. There's some scatter, but overall the model is fairly accurate. In the next figure, predicted versus true initial mass, lies close to the diagonal. There's some scatter, especially for the largest grains, but the backward model still recovers the initial mass distribution well enough to make quantitative inferences from a sampled dust layer.
Putting everything together, our forward model tracks dust grains from 100 kilometers to the surface, incorporating realistic drag, ablation, and wind effects. Using these data, our backward model mathematically approximates the inverse of these dynamics. Together, they demonstrate that surface data retains a quantifiable imprint of the original properties of dust, showing that within our assumptions, it is possible to approximate the incoming distribution from the final distribution.
We implemented our model in Python using SciPy Solve IVP for ODE integration and NumPy and Matplotlib for data analysis and plots. Magnum handles all the animations you've just seen, and we ran everything in Google Colab for reproducibility.
There are still limitations we'd like to explore, like more detailed chemistry, more realistic, time-dependent wind fields, and a full Bayesian inversion from ground dust to entry flux. But this framework already captures the key physics needed for cosmic dust forensics.
Here's the code we used for our core ODEs. And this is the code we used for our stochastic wind model. Here are the main references we relied on.
A special thank you to our mentor, Dr. Gregory Mayer. Thank you for watching our SCUDEM X 2025 submission.